Imagine this: red-hot metal up to 33 feet long, bending as easily as if it were a sheet of paper. Every year, factories all over the world create millions of parts, from car bodies to giant pipes, thanks to bending machines. But how are perfect bends, channels, and even spiral shapes for oil and gas giants born from cold, formless steel? And how can it be done without wasting tons of energy? Let's dive into a world where metal obeys human will. A bending machine. Think of it like a big construction set for metal. Imagine a flat sheet that needs to be bent into a specific shape. The machine takes this sheet and bends it using special tools to get the desired angle or form. First things first, the metal sheet needs to be checked to make sure it's suitable for the required part. This includes checking dimensions and looking for defects like cracks or breaks. The metal sheet is cleaned of dirt and rust using a wire brush or sandpaper. This is necessary to ensure clear marking and subsequent processing. Markings are applied to the sheet using special tools like rulers, squares, and scribers. The layout includes drawing center lines and contour lines, as well as marking the centers for any future holes in the part. To make sure the markings are clear and don't rub off during processing, the metal surface is coated with a special paint. Dry chalk, a chalk solution with glue, or a copper sulfate solution might be used. After applying the markings, they are checked against the part drawing. In large industrial settings, automated systems are often used to lift and place metal sheets onto the machine. These systems might include conveyor lines and robotic arms that precisely position the metal sheet on the machine's bottom die. In smaller workshops, or during small batch production, metal sheets might be placed manually by workers. Workers in protective suits and gloves lift the sheets using special tools or lifting equipment and place them onto the machine. Metal sheets can vary greatly in size, from small ones easily lifted by hand to enormous ones requiring special lifting equipment. In large industrial settings, you might see sheets up to 33 feet long and up to 10 feet wide. Then, the necessary tools are selected: a punch for the upper part and a die for the lower part. These determine exactly how the metal will bend. During the sheet metal bending process, the machine presses the punch onto the sheet and it bends into the die, forming the required shape. This process allows for creating various shapes and angles, depending on the type of punch and die used. The most common method is V-bending, which is used to create angles of various degrees. This shape is widely used in manufacturing elements for construction, machine, and equipment housings, frames, and so forth. U-bending is used to create U-shaped channels from steel and other metals. This shape is ideal for manufacturing metal profiles and channels. Radius bending is used to make parts with cylindrical or conical configurations. Such shapes are used in the production of pipes, cylinders, and other three-dimensional structures. One variation of polygonal bending used to obtain complex shapes is P-bending. Bending sheet metal allows for creating various shapes and angles, but creating a spiral shape is a more complex process. Spiral forms are usually made using special methods and equipment, such as roll-forming machines. These machines are used to produce cylindrical, conical, and other curved surfaces. They allow for creating spiral shapes by sequentially passing the metal through rollers that gradually form the desired shape. Such machines are widely used in the production of pipes, cylinders, and other metal structures that require a spiral form. While roll-forming machines are operating, you can see how metal sheets pass through the rollers, gradually acquiring the desired spiral shape. Spiral forms are used in various industries and everyday applications. They offer high strength, excellent conductivity, resistance to corrosion, and fatigue. Springs, connectors, heat exchangers, electrical engineering and electronics, the oil and gas industry, chemical processing, and medical instruments all use products with spiral shapes. For example, in beryllium copper spiral tubing, the spiral form is used in 50% of applications due to its high conductivity and strength. Spiral cables are used in over 70% of industrial automation systems because of their flexibility and resistance to mechanical wear. Spiral springs are found in over 30% of mechanical drives due to their ability to provide varying spring forces. Spiral pipes, often referred to as coiled tubing, offer several advantages in the oil and gas industry. They can easily adapt to changes in elevation and direction during the transport of oil and gas. This is particularly important when constructing pipelines in complex geological conditions. Coiled tubing has a spiral seam, which facilitates installation. This can reduce assembly time compared to traditional pipes with straight seams. Coiled tubing is used in well clean-out technology after hydraulic fracturing. Nitrogen is pumped through these tubes to wash out proppant from fractures, which increases maintenance intervals and reduces the time needed to bring the well back into operation. Metal forms can be made from various materials, such as steel, aluminum, or copper. The choice of material depends on the requirements for the product and the possibility of reuse or recycling. Traditional manufacturing methods can involve high energy and resource consumption, which can negatively impact the environment. However, modern technologies, like using renewable energy sources and optimizing production processes, can significantly reduce this impact. Metal forms can be recycled and reused, which reduces waste and the need for virgin materials. This is especially important for steel and aluminum products. To protect metal structures from corrosion, powder coatings are often used. These are more environmentally friendly compared to traditional paints because they do not contain organic solvents or harmful substances. Switching to solar, wind, or hydropower can reduce greenhouse gas emissions by 70 or even 90% compared to traditional energy sources. Improving technological processes and automation can reduce energy consumption by 20 or 30% and cut waste by 25%. Reusing metal forms reduces waste by 50 or even 70%. Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white-hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh, right! I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting. Imagine a bearing, larger than a passenger car, that operates without service for 100,000 hours and turns a 5-megawatt wind turbine. Its balls are polished to a precision of 4/millionths of an inch. The melting point of the steel used is almost 3,000 degrees Fahrenheit. Manufacturing it requires factories the size of cities, cranes that lift railroad cars, and presses that squeeze metal like modeling clay. But that's just the beginning. What you are about to see isn't just production. This is industrial magic that holds the whole world together. Where does a giant industrial bearing begin? Not with a blueprint, not even with a machine tool. It all starts with metal. But not just any metal. Special grades of steel are used for bearings, and their chemical formulas are sometimes guarded as trade secrets. Most often, it's chromium or alloy steel with enhanced strength, resistant to extreme pressure, vibrations, friction, water, and even time. The ore from which the steel is smelted arrives from different corners of the globe. It's often extracted through open pit mining, from enormous quarries where dump trucks have wheels as tall as a 2-story house. Then, the ore is delivered to metallurgical plants. These are cities in miniature that operate without sleep or weekends. In blast furnaces, the ore is melted at temperatures close to 3,000 degrees Fahrenheit. Alloying elements like chromium, manganese, and molybdenum are added, and the molten steel is poured into molds, creating large steel ingots. But this isn't a bearing yet. It's just raw material. Next, the ingots are cut into pieces, rolled, heat-treated, and transformed into so-called rings, blanks from which the bearing will eventually be machined. They are transported by special trailers or by rail to machine building plants. A single blank can weigh a ton, and moving it requires a crane. Precision and quality start right here. Any crack, dent, or internal inconsistency, and the entire batch can be rejected. That's why materials undergo rigorous inspection at the factory: visual, ultrasonic, and magnetic particle inspection. The production of a giant bearing forgives no mistakes. Everything must be nearly perfect. Such giant industrial bearings, larger than a passenger car and weighing over 3 tons, are used in heavy-duty equipment. For example, in wind turbines. In the mining industry, huge bearings rotate in crushers, mills, and mining conveyors. In metallurgy, they are used in rolling mills and blast furnaces. Offshore platforms and ships, cement plants, hydroelectric power stations, oil extraction, All require extra-large, super strong bearings. After all, they withstand extreme loads, rotate with immense force, and operate in aggressive environments where smaller parts simply wouldn't survive. After the metallurgical plants deliver the steel ingots, each weighing tens of tons, to the bearing manufacturing facility, the magic begins. These ingots don't have any shape yet, but they already conceal future strength. Giant cranes lift them. One such hoist can support the weight of a railroad car, and with precision down to the inch, lowers the red-hot blank to where they will start sculpting the bearing from it. The scene looks like something from a science fiction movie. Massive hydraulic presses with thousands of tons of force squeeze the metal like modeling clay. It's rolled, pressed, heated again, and it begins to transform into a huge metal ring, rotating on a conveyor. Every movement is accompanied by roars, clangs, and hissing steam. Heating furnaces heat the steel up to 2,000 degrees Fahrenheit. That's almost twice what's needed to melt lead. Workers in protective gear look like characters from a post-apocalyptic movie, and for good reason. One spark could cause serious injury. But thanks to automation and strict safety standards, everything proceeds exactly according to plan. As soon as the ring takes shape, its machining begins. Like a giant potter's wheel, it spins on lathes that, with a screech, shave off layers of metal mere thousandths of an inch thick, grinding the surface to a perfect smoothness. There's no room for error here. Even a tiny inaccuracy can be fatal at the speeds these bearings rotate. Behind every giant bearing stands a team that knows every part of the process inside out. These are engineers, technicians, and master craftsmen who study blueprints, check temperature regimes, lubricate parts on time, and monitor precision down to the micron. Some have worked here for decades. Their hands are covered in grease, their eyes are tired but intense. And despite the noise, the risks, and the difficulty of the work, many wouldn't trade this rhythm for anything. The first massive bearings appeared in the 20th century, when industry began to grow taller and wider. Hydroelectric turbines, rotors in oil refineries, tower cranes, all needed reliable rotators for colossal loads. After grinding comes the most critical part: quality control. The giant bearing undergoes a thorough inspection, like an athlete before the Olympics. Its surface is examined for microcracks using ultrasonic sensors and magnetic particle inspection. The massive ring lies in a special bath, and waves and magnetic particles are passed over it. They'll glow in places where there's even the slightest damage. Then comes balancing. The huge metal structure is mounted on a special stand resembling giant scales. The bearing starts to rotate, slowly at first, then faster. Computers detect any imbalance, and technicians add or remove metal in the necessary places. Everything is done so that in the future, this bearing can operate at tremendous speeds without the slightest wobble. Inside an industrial bearing are steel balls or rollers. Each ball starts as a small metal cylinder, a wire rod, about 1/2 inch to 2 inches in diameter. It's cut into blanks, and then cold heading is used to form the future ball, still with noticeable seams and roughness. At this stage, the blank weighs from 1/10 of a pound to 1.5 pounds, depending on the size. These blanks are called flashes. Next is the tumbling process, where the blanks are passed between two discs spinning at incredible speeds, up to 1,800 revolutions per minute. This removes the seams and achieves a more perfect shape. Then comes heat treatment at 1,500 degrees Fahrenheit to give the steel strength, and only after that, the finest grinding. The balls are ground on high-precision machines with a tolerance no greater than 4/millionths of an inch. Polishing takes 48 hours, and the final result is a ball that can rotate millions of times without wear. A similar process applies to rollers. They are machined from high-strength steel, can be up to 8 inches long, and withstand loads over 10,000 pounds per square inch. They are also ground, heat-treated, and each undergoes individual geometry checks. After manufacturing the rolling elements, it's time for assembly. Between the outer and inner ring of the bearing, a separator is installed, a special cage that evenly spaces the balls or rollers. Separators can be steel, brass, or polymer, depending on the application. For instance, Polyamide cages are often used in wind turbines due to their moisture resistance. A typical bearing for a 5 megawatt turbine might contain around 70 balls with a diameter of 2.5 inches, or 30 rollers 6 inches long. In the final stage, the assembly is lubricated, using grease with an operating temperature range from negative 40 degrees Fahrenheit to positive 400 degrees Fahrenheit. Seals or protective shields are added, and the bearing is ready for work, designed to last 100,000 hours without service. Global leaders in bearing production manufacture enormous volumes. For example, the Swedish company SKF produces 600 million bearings annually. The Japanese company NSK produces approximately 1,250,000 bearings per year. The main challenges facing the bearing industry relate to the high demands on materials and technologies, the need for strict quality control, and the constant implementation of innovations to maintain competitiveness. Fluctuations in global raw material prices, competition in the global market, as well as the need to improve energy efficiency and reduce production costs create additional difficulties for companies in the sector. Ever wonder where your old laptop goes after you toss it out? Every single year, millions of tons of electronics like these end up getting recycled. But hey, it is not just trash. Inside, there is a real treasure trove. Gold, silver, copper. And right alongside that, toxic hazards, mercury, lead, and batteries just waiting to burst into flames at any moment. How do they protect your data on those old drives? Why are the workers dressed like astronauts? See for yourself the shocking but super important journey your old gadget takes, from the conveyor belt all the way to extracting precious metals. It is a sight that will totally change how you think about unwanted electronics. Keep watching. Specialized companies or collection points take in old laptops from regular folks and businesses. The devices get checked to see if they still work. Laptops that are still working might get fixed up and resold, or donated to charities. Large batches of laptops are transported to specialized facilities. There, trucks unload containers full of laptops. Workers using forklifts move them to the sorting area. Then, workers wearing protective gloves and special suits look over each laptop. Yeah, safety is a really big deal here. The people on the sorting line wear protective gloves and suits for a few reasons. Old laptops might have components containing lead, like in the solder, or mercury in the fluorescent backlights of the displays. Touching these without protection could lead to poisoning. Cadmium and beryllium are dangerous if they touch your skin or if you breathe in the dust. These heavy metals are used in batteries and circuit boards. Some laptop parts, especially broken screens, can have sharp edges that could easily cut your hands. And during disassembly, small components can break off and go flying. Even when a laptop seems dead, some capacitors can still hold a residual charge. Touching them without protection could give you an electric shock. Special anti-static suits and gloves prevent damage to electronic components from static electricity. When the laptops are shredded, a lot of toxic dust is created, which can contain microscopic particles of metal and plastic. To avoid breathing this dust in, workers wear masks or respirators. Working laptop models are set aside during sorting. They can be repaired and sold. The rest are sent off for recycling. Lithium-ion batteries are removed by hand because they can catch fire or explode. During shredding, or if they get damaged mechanically, the battery can overheat and ignite. Lithium reacting with air or water can release flammable gases. Also, inside the battery, there are toxic electrolytes that can cause chemical burns or poisoning. If a battery gets deformed, these substances can leak out and get into the environment. That is why workers manually unscrew the panels and take out the batteries. If the battery is built in, they disconnect it using a special tool. The removed batteries are placed into heat-resistant containers filled with sand or other non-flammable materials. They are stored in well-ventilated areas, away from other waste materials. Recycling the batteries happens separately from the rest of the laptop. They go to specialized plants where the metal casings are shredded. From the internal materials, like nickel, cobalt, and lithium, useful components are extracted for reuse. After the batteries, the next critical step is removing the hard drives. Why are hard drives taken out separately? Well, the thing is, even if the laptop does not work, data can still be stored on the drive. And corporate or government laptops might contain sensitive data, so the hard drives have to be destroyed following special procedures. Some drives have moving mechanical parts, like platters and motors, which are processed separately. Other drives are made of memory chips that need a different recycling technology. Workers unscrew the laptop casings and remove the drives by hand. In some models, solid-state drives are built right into the motherboard. In that case, they are either desoldered or broken off along with the board. After that, there are 3 ways they physically destroy the drives to ensure data security. They are either shredded in special shredders, turning them into tiny metal fragments, or they are wiped using magnetic degaussers, which erases the data permanently, or they are melted down into metal ingots. The aluminum casings from hard disk drives are sent off for remelting. The magnetic platters have coatings of gold, platinum, and cobalt, which are extracted using chemical processes. Solid-state drive controllers contain copper, silver, and rare earth metals. These are also extracted for reuse. Once the batteries and hard drives are out, the laptops do not pose a serious fire or data security threat anymore. Now, they can be sent over for automated case disassembly. The laptops move along a conveyor belt, passing one by one under an automated press. Powerful hydraulic plates with up to 5 tons of force squeeze the casing, causing tiny cracks in the fasteners. One hit, and the top panel separates from the bottom, leaving the internal components accessible for further processing. The laptops keep moving down the line. Mechanical arms with thin metal fingers hover over them. Each arm is equipped with an automatic screwdriver unit that spins at up to 5,000 revolutions per minute. In just 4 to 6 seconds, the robot unscrews the screws and carefully removes the keyboard, speakers, and cooling system heatsinks. When the laptop reaches the next module, 2 pneumatic grippers grab onto the screen. A blade with a high-precision control system runs along the edges, cutting through the plastic fasteners. A barely audible crack, and the display is separated. Now the laptop is almost empty, with only the main guts left, the motherboard. Another arm removes it, using vacuum suction cups to lift the board and place it into a separate container. The whole process takes less than 2 minutes, and what was once a whole laptop is now just separate parts, ready for sorting and further recycling. The conveyor moves the separate laptop parts to sorting stations. Both robots and people work here. Plastic case panels are directed one way. They pass through special scanners that identify the type of plastic. Some types of plastic can be reused. Others are disposed of as regular waste or converted into fuel for industrial plants. Metal parts, like case frames, fasteners, and heat pipes, go through magnetic separators. Ferromagnetic metals, like iron and steel, are separated using powerful magnets. Non-ferromagnetic metals, like aluminum and copper, are sorted using induction detectors. Glass from the display screens goes into a shredder, where it is broken into small fragments. After that, special equipment cleans the glass granules of impurities. The resulting material can be used to make new displays or building materials. Motherboards, graphics chips, processors, and other integrated circuits are collected separately. They are checked to see if they can possibly be reused. If the circuits are still usable, they are sent to the secondary market or for refurbishment. Most electronic components, however, end up being recycled. To do this, they are sent to special furnaces where high temperatures burn off the organic materials. Only the metals remain: gold, silver, copper, palladium. They are extracted using chemical methods, purified, and returned to manufacturing. Laptops also contain hazardous substances: lead, mercury, cadmium, lithium. These cannot be allowed to enter the environment, so they undergo special processing. The fluorescent lamps from displays, which contain mercury, are separated under sealed conditions so that mercury vapor does not escape into the air. The recovered mercury is reused, for example, in medicine or in making thermometers. The lithium batteries, which were removed in the initial stage, are transported to separate plants. There, they are dismantled and lithium and other useful elements are extracted. The resulting materials are used in the production of new batteries. Lead, found in solder, is melted down under controlled conditions, separating it from impurities. The entire process of dismantling, sorting, and recycling a laptop can take anywhere from a few hours to several days, depending on the scale of the facility and the technological process used. After sorting, all the materials are distributed into separate containers, or large industrial bins, depending on their type and the next steps in processing. In the plastic containers, you will find fragments of casings, keyboards, touchpads, which might be black, gray, or silver. The plastic is sorted by type: acrylonitrile butadiene styrene, polycarbonate, polypropylene. In the bins for metals, you can see piles of parts. Here lie aluminum frames and lids from laptop cases, copper heat sinks and wires, steel fasteners and screws. Containers for electronics are filled with the removed motherboards, graphics chips, random access memory modules. It all looks like a heap of complex green and blue boards with gold contacts and copper traces scattered across them. In separate containers for displays, there are dismantled screens with fragments of glass and metal frames. Sealed containers for hazardous materials hold batteries. Mercury lamps and capacitors containing lead are stored separately. These are often kept in special zones with warning signs about toxicity and explosion risks. After sorting, all these materials need to be transported to specialized plants where they will undergo further processing and preparation for reuse. To save space in trucks and containers, some materials are compressed. For example, plastic is shredded into granules or pressed into large bales. Metals are compressed into dense cubes. Glass is crushed and packed into bags or containers. Electronic components are stored in large containers without being compressed, since they still need to undergo chemical treatment. Lithium batteries are placed in special non-flammable containers, often filled with sand or expanded clay pellets to prevent ignition. Mercury lamps are transported in sealed boxes that prevent mercury vapors from getting into the air. The materials are loaded onto trucks, trains, or ships, depending on the distance and the type of material. Large metal cubes are lifted by forklifts and stacked in trucks. Containers with plastic and glass are transported in trailers or sea containers. Electronic components might be transported in special containers with shock-absorbing protection. Metals are sent to metallurgical plants, where they are melted down and purified. Aluminum, copper, and iron can be reused in manufacturing electronics, cars, or building materials. Plastic goes to plastics recycling plants, where it is shredded, melted down, and used to produce new casings for electronics, furniture, or packaging. Glass goes to facilities that manufacture new screens or building materials, for example, insulation made from recycled glass. Electronic circuit boards are delivered to plants specializing in extracting precious and rare earth metals. There, the integrated circuits are dissolved in chemical solutions to extract gold, silver, palladium, and other valuable metals. Batteries head to facilities where lithium, nickel, and cobalt are extracted for manufacturing new batteries. Hazardous waste goes to special landfills or chemical plants, where toxic substances are neutralized or rendered harmless under controlled conditions. After several months or even years, the materials from a recycled laptop can end up back in production, as part of a new device, building, or car. Some large recycling facilities specialize narrowly, for example, dealing only with computer equipment or mobile devices. Others recycle almost all types of electronics, including large household appliances. Every year, the United States spends $17 billion just on importing fresh fruits, and avocados from Mexico alone rack up $3 billion of that. The sugar in your cup of tea? Chances are, it traveled thousands of miles from Latin America. Americans chow down on 1 billion pounds of tuna every year, and 90% of winter tomatoes come from Mexico, where agricultural cartels are battling it out for control of that market. From olive oil out of Spain to turmeric from India, imports keep the United States fed with variety and savings. In this video, we're going to spill the beans on where your favorite foods come from, the numbers behind their journey, and why it matters to every single one of us. Don't miss it. It's going to be tasty and full of surprises. Get comfy. Brew yourself some tea. Do you take it with sugar? Well, that sugar probably came from another country just for you. Even though the United States produces its own sugar, demand often outstrips supply, making imports a must. The United States is a huge sugar consumer. Plus, producing sugar in some countries is cheaper thanks to better climates and lower costs, which makes importing a smart move. The big players supplying sugar to the United States are countries in Latin America and the Caribbean, especially Mexico, which gets a sweet deal on the American market thanks to the North American Free Trade Agreement. Closing some borders in 2025 wasn't meant to mess with legal trade between the United States and Mexico. Still, it might have slowed down logistics and caused delays in getting goods like sugar across. The European Union is a key supplier of seafood to the United States of America, keeping the American market stocked with all kinds of fish and shellfish. This helps meet demand for seafood in the United States and keeps the supply steady. Spain and Japan are major players when it comes to fresh and frozen tuna for restaurants. Tuna is one of the most popular seafoods in the United States. Americans eat about 1 billion pounds of it a year. That makes the United States one of the world's top tuna consumers. Thailand, Indonesia, and Vietnam are the go-to sources for canned tuna, the most affordable and in-demand option. You'll find it in salads, sandwiches, or just as a quick snack. French oysters and other shellfish are a hit with American eaters too. The Netherlands pitches in with fish shipments to the United States as well. Every year, the United States shells out more than $17 billion just on fresh fruit imports. The biggest supplier? Mexico, covering over 40% of all fruit imports to the United States. Importing means supermarkets can offer a huge variety of fruits no matter the season. Americans eat more mangoes, pineapples, and avocados than they can grow at home. Plus, bringing them in from countries with cheaper labor often beats growing them domestically. Take avocados. Mexico supplies over 90% of the avocados imported to the United States. Each year, Mexican farmers ship over 2,640,000 pounds of avocados to the American market, worth about $3 billion. Most of those avocados come from Michoacán, where the climate's just perfect for growing them. Every year, the United States imports over 880,000 pounds of olive oil, costing around $1,500 million. Demand's climbing thanks to the Mediterranean diet craze and the push for healthy eating. Drop a comment below. Do you go for healthy eating too? Meanwhile, American producers, mostly in California, are trying to ramp up their own olive oil output, but it's still a drop in the bucket compared to Europe. Spain leads the pack, supplying over 40% of the olive oil imported to the United States. Spanish oil's a favorite for its quality and decent price. Italy, which used to rule the American market, now sits in second place with about 30% of imports. Greece and Tunisia are stepping up too, especially in the premium oil game. The most popular cheese in the United States? Mozzarella. It makes up about a third of all cheese eaten here, thanks to being the star of pizza, one of America's favorite foods. Cheddar's a close second, showing up in sandwiches, burgers, and mac and cheese. The United States churns out over 13,200,000 pounds of cheese a year, but it still imports premium kinds too. Top suppliers include Italy, France, the Netherlands, Switzerland, and Spain. Each year, the United States brings in over 352,000 pounds of cheese, worth about $1,500 million. Most of it ends up in restaurants and gourmet shops since real European cheeses cost a pretty penny here due to tariffs and shipping. Parmesan's a big name and a fan favorite in the United States. The country imports over 22,000 pounds of it yearly, though a lot gets used pre-graded. The real Parmigiano Reggiano's pricey, so the local knockoff, Parmesan, made with simpler methods, is way more popular. 70% of tomato imports come from Mexico. Mexico supplies nearly 100% of the fresh winter tomatoes in the United States since its climate lets them grow year-round, while American production tanks in the cold months. US farmers grumble about cheap Mexican tomato imports, and trade spats between the two countries have flared up more than once. Most of those tomatoes roll in through Florida, but they compete hard with local ones, putting political heat on the US government to cap imports. Texas border crossings handle millions of tomato crates every year. For example, over 50,000 trucks loaded with tomatoes pass through Laredo alone annually. Mexico sends over tons of cherry and Roma tomatoes, loved by Americans for their sweetness and cooking convenience. Oh, and in Mexico, powerful agricultural cartels run the tomato show, sometimes sparking criminal showdowns over market control. Canada's the third biggest food supplier to the United States, trailing only Mexico and the European Union. What do you think? Could we lose such a major importer anytime soon? Key categories include meat, grains, dairy, fish, and veggies. Canadian pork exports to the United States top $2 billion a year. Canada's also a big beef supplier, especially after mad cow disease caused some hiccups. But chicken? Nope, Canada's not sending that over. A bird flu outbreak wiped out poultry and slashed egg supplies big time too. Being right next door, Canada cuts down on shipping costs for the United States. Plus, their quality standards match what the American market demands. China sends a hefty chunk of food to the United States, though it's a smaller slice of their imports compared to electronics or clothes. China's a top seafood supplier, especially tilapia, shrimp, cod, and canned fish. It's also the world's biggest garlic grower, and a lot of that heads to the United States. Then there's green tea, black tea, and honey coming over too. Americans love Chinese rice noodles, sweet potato vermicelli, and wheat noodles. Demand for Asian foods has shot up over the last few decades, thanks to Asian restaurants, street food, and the healthy eating trend. Rice and sweet potato noodle consumption in the United States is up 20% in the last 10 years, driven by the gluten-free craze. The United States is one of the biggest importers of Indian spices. Top picks include turmeric, cardamom, cumin, coriander, chili pepper, and cloves. India produces over 80% of the world's turmeric, and a big chunk of that lands in the United States. Oh, and India is the second largest tea supplier to the United States after China, with faves like Assam, Darjeeling, Nilgiri, and masala chai. India is the main source of basmati rice for the United States too, perfect for healthy eaters and Indian food fans. The United States brings in tens of thousands of pounds of legumes from India yearly as vegetarian diets catch on. Mangoes? A total crowd pleaser. India ships over 33,000 pounds a year. Demand for Indian goods is booming thanks to healthy eating trends, exotic flavors, and the rise of Indian cuisine in the United States. You might wonder, why all this importing? Doesn't the United States grow broccoli or spinach? Sure, but don't forget those harsh winters in some regions. Imports dodge seasonal shortages, keep prices down, and bring variety. In summer, California, the United States' veggie powerhouse, has huge harvests, but winter cuts production way back. Cheaper labor abroad helps too. Growing and freezing veggies in places like Mexico, China, or Peru costs less than doing it in the United States. It's easier to ship frozen veggies over. They last longer and keep their nutrients, making them perfect for restaurants and big stores. Take broccoli. It holds on to its goodness when frozen. It's a legit superfood, packed with nutrients and proven health perks. Even though the United States is a top tofu exporter, it imports plenty too to meet demand. About 1,585 importers bring tofu into the United States, keeping the market stocked with options. Tofu imports have doubled in recent years. Made from soybeans, it's a protein-packed powerhouse. Tofu's a big deal in global trade, thanks to its nutrition and appeal to all kinds of eaters. The United States plays both sides as a major exporter and importer, showing how much Americans crave it. Beyond foodies and health nuts, athletes and bodybuilders dig tofu too. It's clutch for building and recovering muscles. Every year, the world produces over 10,000 tons of titanium discs, the material used to create the hearts of airplanes, implants for surgeries, and even parts for spacecraft. A single disc can weigh more than a smart car, but it fears neither temperatures of 1,800 degrees Fahrenheit nor the vacuum of space. How does a gleaming superdisc, capable of withstanding thousands of revolutions per minute, emerge from a gray, spongy mass? What do aviation, medicine, and the titanium hell of furnaces have in common? This isn't just manufacturing, it's a show of strength, precision, and engineering magic. Let's dive into a world where metal takes on its perfect form. Titanium discs are blanks shaped like thick discs made from titanium or its alloys. They serve as the starting material for parts in highly critical fields: aviation, medicine, space, energy, and automotive manufacturing. Titanium is a true superhero among metals. It's lightweight yet extremely strong, withstands insane temperatures, resists corrosion, and doesn't react with the human body. That's why it's used for everything, from aircraft components to implants. But pure titanium is a bit finicky. It's difficult to machine and can be brittle under certain conditions. Therefore, it's often mixed with other elements, creating alloys. The most popular alloy consists of titanium with 6% aluminum and 4% vanadium. It's strong, wear-resistant, and easier to form. Aluminum adds lightness and heat resistance, while vanadium adds flexibility. For medical devices, pure titanium or alloys without toxic elements are used. Depending on the task, titanium can be harder, more ductile, or more resistant to extreme conditions. That's why manufacturers choose not just titanium, but the specific alloy that perfectly meets the particular challenge. Titanium for discs comes from titanium sponge, the primary raw material extracted from ores, mainly ilmenite and rutile. The largest deposits of these ores are found in Australia, South Africa, China, Kazakhstan, and Canada. But the sponge itself is produced where complex manufacturing facilities exist because the process of converting ore into metal is very energy intensive. It all begins with a dirty grey, pumice-like substance, titanium sponge. It arrives at the plant in large containers and bears almost no resemblance to the future aerodynamic part. But this is where the journey starts, ending with the gleam of a perfectly polished disc capable of withstanding thousands of revolutions per minute. First, it's checked for impurities and moisture. Acids or solutions that react with impurities are used, removing them from the titanium surface. This process might involve treating the raw material in special baths. Titanium parts might also undergo abrasive treatment, such as grinding or sandblasting, to remove surface contaminants. After cleaning, the titanium raw material undergoes heat treatment to improve its structure. The raw material is heated to a specific temperature, usually between 1,300 and 1,600 degrees Fahrenheit, and held there for a defined period. This helps reduce internal stresses that might have occurred during previous processing stages. If necessary, the raw material can be heated to higher temperatures to achieve homogeneity in the alloy structure. This ensures an even distribution of elements within the material, enhancing its strength. After heat treatment, the titanium undergoes a fascinating rapid cooling stage, which is quite a spectacle. When the metal is removed from the furnace, it glows with bright shades of red and orange, reflecting the high temperature it was heated to. Cooling can be done in several ways, by quenching in water or by air cooling. When submerged in water, you can observe the hot titanium creating foam and bubbles as it rapidly contacts the liquid, emitting a characteristic crackling sound. This is visually impressive, as the boiling water witnesses an incredible transformation, from a potentially malleable state to a strong metal. Alternatively, air cooling is calmer, but no less captivating. The metal gradually loses heat, changing its color and texture. This process, although less dramatic, demonstrates the smoothness and elegance of titanium's transition to its final form. Then, the material is loaded into special crushers or hammer mills. The main purpose of crushing is to reduce the particle size of the titanium, facilitating further processing and ensuring material uniformity. The crushed particles can be used in various processes, such as producing powder alloys or forming new parts. After crushing, The resulting particles may be washed to remove residual debris or impurities. They are then dried in preparation for further processing. To manufacture the titanium discs themselves, the blanks are heated to high temperatures, typically up to 1,500 or even 1,800 degrees Fahrenheit. This is done to make the titanium softer and easier to work with. The heated blank is placed in a press or hammer. Impact action or pressure shapes the blank into the desired disc form. During this process, the titanium undergoes significant deformation, leading to changes in its structure. For casting, however, special molds are made, usually from steel or cast iron. The molds must be very precise to ensure the correct geometry of the disc. The titanium is heated until it turns into a liquid. This is usually done in vacuum furnaces to prevent oxidation. The liquid titanium is poured into the prepared mold. After cooling, it solidifies, taking the shape of the disc. Casting allows for the production of discs with complex shapes that are difficult to achieve by forging. Now it's time for machining. Before machining, the discs are cleaned of dirt and residues. For this, they are immersed in a special bath with a solution that removes slag and grime. The water foams up, and the disc becomes clean. Next, the discs are secured on lathes for stability during machining. A lathe is used to remove material from the edges of the disc, achieving the required diameter. Thin metal shavings curl away from the cutting tool like a slender snake. The contours and profiles of the disc are formed according to technical specifications. If grooves or holes are needed, a milling machine is used. Then, the discs are processed by grinding machines to achieve the smoothest possible surface. This is important for reducing friction. Finally, they are polished to obtain a shiny surface, which also enhances their aesthetic qualities. Polishing can further protect the disc from corrosion. After polishing, the surface becomes smooth, reducing the likelihood of dirt and moisture accumulation. Fewer imperfections and cracks mean fewer chances for corrosion. Polishing also seals microscopic pores that can retain moisture and contaminants. This significantly reduces the risk of oxidation. Afterward, the disc is inspected for scratches, cracks, or other visible defects. Calipers and micrometers are used for precise measurements of the disc's diameter and thickness. To detect internal defects not visible on the surface, ultrasonic testing is performed. This inspection method does not require direct contact with the disc. A special transducer emits ultrasonic waves into the disc material. As the waves travel through the disc, they reflect off boundaries such as defects or the material itself. The time it takes for the waves to return to the transducer is measured. This allows for the detection and sizing of defects. Specialized software analyzes the received data, providing information about the disc's condition. This is a very fast process, allowing many discs to be checked quickly. Titanium is 40 times lighter than steel, but has comparable strength, making it ideal for the aviation and automotive industries. It does not rust or corrode in most environments, making it a durable choice for various applications. In the United States, an average of 10,000 to 15,000 tons of titanium is produced annually. A significant portion of this amount is used for manufacturing discs and other components. Thus, on a monthly basis, this could amount to 800 to 1,200 tons of titanium discs. Leading companies in the United States, such as Boeing and Lockheed Martin, actively invest in the production of titanium discs to meet the needs of their programs. It is expected that in the coming years, the demand for titanium discs for aviation will grow by 5 to 7% annually, especially considering new technologies and increased aircraft production. Every single year, more than 170 million old refrigerators are disposed of throughout the world. However, what actually happens to them once they disappear from our kitchens? Refrigerants that can damage the ozone layer, hundreds of pounds of metal, plastic, and even precious metals all require specialized processing. Did you know that old refrigerators contain gold, silver, and copper that can all be given a second life? And some models are even sold to poorer countries instead of being recycled. Please stay with us to see how junk is turned into a resource and discover who is making millions of dollars in the process. In the United States of America, there are several ways old refrigerators are collected for disposal, ensuring safe and environmentally responsible recycling. Some large retail chains, such as Best Buy, offer programs to recycle old household appliances. When you purchase a new refrigerator, they can take the old one away for further recycling. These programs often come with restrictions, for example, no more than 3 appliances per day from a single household. There are a few reasons for limits on how many appliances can be recycled. The first reason is logistics and the burden on the system, since recycling centers have limited capacity. If everyone could drop off any number of appliances, the collection and recycling processes could become overloaded. These programs are also intended for individual consumers, not for businesses or resellers. The limits also prevent hauling companies from making free use of disposal services. The third reason concerns cost optimization. In many cases, recycling is subsidized by the government or by private companies. The restrictions help control expenses and distribute resources evenly. The final reason is environmental responsibility. These programs often encourage people to switch to energy-efficient devices rather than simply throwing away large quantities of appliances. It is a kind of balance between convenience for consumers and the operational efficiency of the recycling centers. In many cities and districts, there are municipal collection points for large household appliances. Consumers can bring their old refrigerators to these points, where specialized companies pick them up for recycling. These collection points can be stationary or mobile, which makes it more convenient for residents. Some energy companies also offer programs for disposing of old, inefficient refrigerators. They may provide financial incentives or free appliance removal to encourage consumers to switch to energy-saving models. There are also private companies that specialize in collecting and recycling large household appliances. They offer services to remove old refrigerators directly from the consumer's home for a certain fee. These methods of collecting old refrigerators support the responsible handling of electronic waste, ensuring proper recycling and minimizing negative impacts on the environment. After collection, old refrigerators are taken to specialized recycling centers, where they are sorted and prepared for disposal. This process unfolds in several main ways, which we will describe right now. Many major cities have specialized facilities that accept old appliances directly. For instance, in the United States of America, such facilities operate under programs focused on the responsible recycling of electronics. In some situations, refrigerators are first sent to warehouses or designated lots where enough units are accumulated for subsequent mass recycling. This saves on transportation costs and streamlines logistics. Some large brands, such as Whirlpool or LG, run their own recycling programs. They take back old refrigerators, break them down, and reuse some of the materials in the production of new appliances. Sometimes, old but still functioning refrigerators are sold or transferred to less developed countries. This practice is considered controversial because such equipment can consume a lot of energy and may contain hazardous substances. How do you feel about this issue? Is it better to have a refrigerator that poses potential harm, or is health more important than questionable humanitarian aid? In Europe, there are strict regulations regarding the recycling of household appliances. For instance, under the Waste Electrical and Electronic Equipment Program, refrigerators are transported to certified centers, where they are taken apart into environmentally safe components. At every stage of this process, safety regulations must be observed, because refrigerators contain refrigerants and other potentially harmful substances that cannot simply be dumped in a landfill. Before a refrigerator is sent for dismantling, its technical condition is assessed. Models that still work can be repaired and resold, or donated to charitable organizations. Faulty or obsolete models are immediately directed to further processing. Next, refrigerators are categorized, since different models contain different materials and refrigerants. They are divided into industrial refrigerators, household refrigerators, and refrigerators containing harmful freon. After that, refrigerators are checked for the presence of hazardous gases and liquids. Freon and other refrigerants are removed because they require special disposal methods, as they deplete the ozone layer. Lubricants are drained, since they can contain heavy metals. Before extracting freon, technicians place the refrigerator in a designated treatment area, where they check which specific refrigerant is used. Technicians connect the refrigerator to a vacuum pump, which creates pressure inside the system and forces the Freon to flow in the required direction. The refrigerant is drawn out through specialized valves, after which the gaseous Freon is collected in sealed containers, while the liquid Freon is filtered and can either be used again or sent for chemical recycling. The Freon that is collected undergoes purification to remove oil, moisture, and metal particles. After that, it is either destroyed or reused in cooling equipment. Older banned refrigerants must not be released into the atmosphere, so they are incinerated in special high-temperature installations that break them down into harmless components, or they are converted into newer, safer gases through chemical reactions. All of this happens at certified facilities because mishandling Freon can cause damage to the environment. Once the Freon and other refrigerants have been dealt with, it is necessary to drain the lubricants from the refrigerator. These fluids contain pollutants that can harm the environment. The lubricant in a refrigerator is mostly in the compressor, which is responsible for circulating the refrigerant. During operation, it mixes with Freon, so removing both substances often occurs simultaneously, although it depends on the specific model. Before draining the lubricant, the compressor is removed or punctured so that the fluid can flow out freely. The lubricant then either drains by gravity into a collection tank, or it is pumped out by a vacuum device. Special containers are used to prevent spills and the evaporation of dangerous substances. The collected fluid is then purified of any remaining Freon, metal particles, and other impurities through settling and filtration. After purification, the lubricant can be reused in compressors if additional cleaning is performed. If it cannot be recycled, it is incinerated in special furnaces. It can also be applied in certain industries, for instance, in the production of technical lubricants. This is carried out at specialized facilities to prevent leaks of harmful substances into the environment. Modern refrigerators contain electronic boards, displays, and battery elements. Workers remove these parts by hand because automated conveyors cannot handle such components without damaging valuable materials. Prior to shredding, refrigerators undergo inspection. Wiring, plastic parts, and insulating panels are taken off. These materials are sorted for further recycling or safe disposal. In general, human oversight is required at every step to ensure safe and clean disassembly. However, certain processes are automated. For example, shredding metal housings or compressing plastics. The external body of a refrigerator is usually made of steel or aluminum sheet. It is separated either by hand or by hydraulic machines and sent for shredding. Compressors and condensers have a high content of non-ferrous metals, such as copper and aluminum, so they are taken apart separately. Copper and aluminum are then sent for smelting and used in new electric devices. Refrigerators also contain many plastic parts, such as internal panels, shelves, bins, and door gaskets. Workers remove these elements by hand because the plastic must be sorted by type. Certain types of plastic are recycled into pellets, which are later used to manufacture new products. Some refrigerator models feature glass shelves or glass doors in display-style refrigerators. This glass is removed manually, sorted by quality, and sent for remelting. Modern refrigerators include control boards, displays, wiring, and batteries. Electronic parts are taken out and transferred to specialized facilities for extracting precious metals like gold, silver, and palladium. Most refrigerators have foam polyurethane or polystyrene foam as insulation. It is removed or shredded, and some of that material can be used as filler in construction or for manufacturing new insulation. Metals go to metallurgical plants. Plastics are compressed into briquettes and sent to recycling facilities. First, the plastic parts, meaning bins, shelves, and outer components, are placed into special shredders. Inside these machines, blades or rotary cutters chop the plastic into tiny pieces no more than 2 inches in size. Next, the plastic fragments are washed in water baths to remove dust, adhesive residue, labels, and other impurities. Some plastics undergo separation, during which they are divided by density. For example, lighter polymers float to the surface, while heavier ones sink to the bottom. The cleaned plastic is sent through powerful drying units to ensure it has no excess moisture. since moisture can reduce the quality of the recycling process. The dried plastic is then fed into hydraulic or mechanical presses, where it is compacted under pressures of up to a few hundred short tons. This process occurs without heating, so the material does not melt, but simply becomes more dense. The pressed plastic is formed into briquettes weighing from a few pounds to a few dozen pounds, depending on what clients need. The finished briquettes are wrapped in film or secured with metal straps so that they do not fall apart during transport. They are then shipped to factories, where the plastic will be melted and converted into new items such as plastic containers, furniture, pipes, or even parts for new refrigerators. This method conserves space during transport and reduces logistics costs, since pressed plastic occupies several times less volume than loose fragments. Glass is remelted and used in new glass products. Electronic parts are recycled separately, and precious metals are extracted from them. Insulation materials are partly disposed of or reused. Thanks to modern technology, most materials from old refrigerators get a second chance at life. Every single year in the United States, millions of cucumbers are pickled, and it is truly an artistic process. Have you ever stopped to think about how exactly that happens? All those jars of cucumbers lining the supermarket shelves, from the very first to the very last, have been harvested, processed, packed, and delivered, so they can end up right in your hands. So, let us peek behind the scenes together and discover how a full-cycle plant carries out this remarkable process. In the United States, some pickling plants operate their own plantations, where cucumbers are grown specifically for this purpose. It is not just about harvesting, it is also about ensuring that each cucumber has the perfect size and shape. This is no accident. Every cucumber that arrives at the plant must meet strict standards, or the pickling will not be as effective. For example, in the state of Michigan, which is home to one of the largest cucumber pickling companies, the plantation area can span 5,000 or even 10,000 acres. This allows for the cultivation of millions of cucumbers every year. Plants that specialize in pickling handle enormous production volumes. A single plant can process up to 100 million pounds of cucumbers per year. The exact amount depends on the size of the facility and the region. In order to maintain a stable supply to the market, these plantations often have contracts with farmers who grow cucumbers specifically for pickling. Ultimately, from harvest through processing, everything revolves around massive scale. These cucumbers typically measure from about 3 to about 5 inches in length, and their shape must be smooth, without bends or defects. This is important, since crooked or overly large cucumbers will not only look unappealing on store shelves, but can also harm other produce during processing, affecting the overall shelf life. Various technologies are employed on these plantations to ensure uniform cucumber size. For instance, they rely on controlled growing conditions, proper temperature, irrigation, and fertilizers, and row-based planting to avoid excessive competition among the plants. Additionally, automated sorting systems examine each cucumber to confirm it meets the required standards. This makes it possible to remove all imperfect specimens before they ever make it to the pickling stage. Full-cycle pickling plants are not just simple production sites where someone takes a jar and fills it with cucumbers. Rather, they are large-scale complexes in which everything, from gathering the cucumbers, through cleaning them, to packaging and labeling, is done under one roof. Picture vast areas that include not only production lines, but also specialized storage chambers for fresh vegetables, which must remain in pristine condition right up to the moment of pickling. Furthermore, such plants usually have laboratories to monitor product quality at every step. Hence, even when you buy a jar of cucumbers, you can be sure the production process has undergone rigorous scrutiny. As you can see, it is more than just a jar on a shelf. It is the end result of an entire industry that works at every level. The process of harvesting cucumbers on these specialized plantations is quite a spectacle, bringing together manual work and high-level technology. Initially, workers go into the field with baskets or special containers for collecting cucumbers. It is a delicate job because every single cucumber must be plucked by hand so the other plants are not damaged. In the past, harvesting was almost entirely manual. But as technology has advanced, more mechanical methods have been introduced. Nonetheless, workers still check each piece for ripeness and shape. On larger plantations, machines are frequently used to gather cucumbers. These machines feature special drums or vibratory mechanisms designed to collect the cucumbers without harming them. They move along the rows, carefully picking the produce. Although mechanical harvesting is faster, it requires constant supervision to minimize damage. Once harvested, the cucumbers often undergo an initial inspection right in the field. This might include basic sorting by size and shape, filtering out any cucumbers that fail to meet the standards for pickling. Certain plantations use automated systems to do this sorting. Immediately after harvest, cucumbers are transported to the plant for further processing, so their freshness is preserved. All of these steps are carried out very quickly, minimizing the time between picking and processing. Plantations often employ refrigerated trucks to keep the cucumbers from overheating. Now comes the most fascinating part. How exactly do cucumbers land in jars? It begins with washing and sorting. After harvest, cucumbers are thoroughly washed and checked for defects. The washing tanks can hold from about 11 to about 17 short tons of cucumbers at any one time, which is like a whole pool filled with these crispy green fruits. Often, long stainless steel baths are used, where the cucumbers travel along a conveyor belt fully immersed in water. They are first placed in a large water tank for soaking, which loosens soil and leaves. Air bubbles are introduced into the water to gently shake the cucumbers, removing dirt in a way that mimics the gentle motion of a natural stream. This helps avoid mechanical damage. Following the soak, cucumbers pass under strong shower units that rinse away any remaining residue. The water pressure is high, yet carefully managed so the delicate surface of the cucumbers is not harmed. Afterward, they roll across rows of soft rotating brushes, which remove any fine bits of dirt and give the cucumbers a clean, market-ready appearance. Clean cucumbers undergo a final check. Either cameras or employees examine their condition, looking for any defects, rot, or damage. The water used for washing is circulated through multiple rounds of purification and filtration. Many plants feature systems for reusing water, thereby reducing environmental impact. Only the best cucumbers move on to the next stage: slicing, pickling, and packing into jars. The pickling solution is not merely vinegar mixed with water. It is a carefully formulated combination of various spices, salt, and sugar that yields the cucumber's distinctive taste. Here too, there are secrets. The solution is prepared according to an exact formula specifying the precise amount of each ingredient. Following the washing stage, cucumbers travel by conveyor belt toward the slicing machines. Before slicing, they pass through a laser scanning system that measures their length and shape, ensuring uniform pieces. The slicing itself is performed by rotating stainless steel blades that spin at more than 300 revolutions per minute. The machine can be set for different slicing styles: rounds, strips, or halves, depending on the type of pickles being produced. In 1 minute, a single line can slice and prepare for pickling over 1,100 pounds of cucumbers. The cucumbers then proceed into a large tank, where they are evenly bathed in a hot pickling solution. The makeup of this solution can vary, but it generally includes water, vinegar, salt, sugar, and spices. Special nozzles guarantee thorough distribution of the liquid among all the cucumbers. The cucumbers advance to a specialized conveyor system where robotic manipulators precisely fill each jar. The nozzles measure out the exact amount of pickling solution for every jar. In the final stage, jars pass beneath a presser, which applies lids and hermetically seals them. One production line can handle up to 300 jars per minute. The accuracy of dispensing the pickling solution is calibrated down to the milliliter, ensuring no jar is overfilled. The pickling solution is drawn from dedicated reservoirs through a network of pipes that maintain a constant temperature of around 200 degrees Fahrenheit, thereby sterilizing the jars and prolonging shelf life. Any leftover solution returns to the reservoirs for reuse, which reduces costs. After each recipe change, the equipment automatically undergoes a hot water and steam rinse, ensuring everything remains pristine. Lids come in from a dedicated feeder system, where they are oriented and sent out precisely in sync with the jars on the conveyor. The lids are pressed firmly onto the top of each jar so that an airtight seal is achieved. The lid temperature can be kept at up to about 160 degrees Fahrenheit to aid in forming a secure seal. Sealed jars then move on to a separate conveyor, where labeling is done automatically. 600 labels can be applied per minute. Laser or thermal inkjet printers mark the expiration date and batch number directly on the label or lid. Cameras check label quality, and if any jar has a crooked or missing label, it is automatically diverted for another labeling cycle. In a single 8-hour shift, the plant can seal and label over 192,000 jars. Why are these pickles so delicious and always fresh tasting? Here is the key. Every step, from selection and growing to processing and packaging, is focused on preserving the natural taste of the cucumber while making the product both safe and flavorful for you. Everything is conducted in a manner that ensures efficiency and upholds the strictest quality standards. Thus, in this process, which is driven not only by technological innovation, but also by genuine passion and skill, you can witness true artistry. Each step, from planting the cucumbers to pickling them, deserves special attention. Indeed, even the way the jar looks on the shelf stems from the dedicated work of many individuals who keep refining this process day by day. Every year, between 80 billion and 150 billion units of Adidas clothing are produced worldwide. But what about footwear, which holds the second largest production volume in the world? Recently, Adidas has seen a significant surge in popularity for its retro models, such as Samba, Campus, and Handball Special. According to the online platform StockX, Adidas sales increased by 51% compared to the previous year. Let us dive into the production of these legendary sneakers and see how new footwear is brought to life. The process of creating a new Adidas shoe model begins long before the first physical samples reach the production line. Dozens of specialists from different fields take part in this process. Designers, marketers, engineers, technologists, and even sports consultants. Adidas designers constantly analyze market trends, researching which models are currently in demand, which technologies are evolving, and what consumers prefer. This includes analyzing past sales data, studying fashion trends in streetwear and sportswear, monitoring competitors such as Nike, Puma, and New Balance, tracking new materials and innovations in manufacturing, and conducting surveys with professional athletes and regular users. This process can take anywhere from several weeks to several months, depending on whether it involves updating an existing line or creating an entirely new concept. Once the team gathers enough information, the concept development phase begins. Designers create the first sketches, plan the shape, position logos, and select material and color combinations. At this stage, it is crucial to find the perfect balance between style, functionality, and comfort. Interestingly, Adidas frequently uses specialized three-dimensional modeling software that allows designers to create realistic digital images of future shoes. This helps save time and provides a more accurate visualization of how the model will look in reality. This exciting process can involve anywhere from 10 to 50 people, depending on the complexity of the project. This includes not only designers, but also biomechanics specialists who assess comfort and foot impact, technologists responsible for materials, and even marketers who propose changes to meet consumer expectations. Designers may suggest a stylish solution, but if it is uncomfortable or does not meet technical requirements, such as weight, material durability, or breathability, it must be revised. Some ideas are impossible to implement due to technological constraints or excessively high production costs. Adidas is actively working to reduce environmental impact using recycled materials and eco-friendly technologies, which also influence design decisions. After the first physical prototypes are created, Adidas puts them through rigorous testing to evaluate comfort, durability, and compliance with stated characteristics. This stage assesses material quality, seam strength, and overall resilience before launching the model into mass production. Shoes are placed in specialized machines that simulate walking or running through thousands of cycles to test the wear resistance of the sole and upper materials. The sole bends thousands of times to check for cracks or deformations. The shoes are submerged in water or exposed to moisture to test their resistance to soaking. The force required to tear fabric, seams, or glued elements is measured. Adidas employs robotic systems that replicate real-life usage conditions. Special robots simulate foot movements during running, jumping, and sharp turns. Shoes are subjected to extreme temperatures to assess material behavior. Shock absorption and impact resistance are analyzed using sensor platforms. No footwear enters mass production without undergoing real-world testing. Adidas collaborates with professional athletes who wear new models during training and provide feedback. Key testing aspects include comfort during running, jumping, and prolonged wear, foot and ankle support, breathability, and adaptation to different surfaces such as asphalt, grass, and hardwood floors. All these stages can take anywhere from several months to a year, depending on the model's complexity and the number of necessary adjustments. If a prototype fails testing, it returns for further refinement. Adidas works with suppliers worldwide. For example, the Boost sole was developed in collaboration with the German chemical company BASF. This revolutionary sole consists of thousands of expanded thermoplastic polyurethane pellets that provide high energy return. Once all necessary materials arrive at the manufacturing facility, one of the most crucial stages begins: cutting and preparing shoe components. From large fabric or leather rolls to sheets of synthetic materials, all components are placed in designated cutting zones. Workers or automated systems load materials into cutting machines according to the production plan. Modern Adidas factories use automated feeders that evenly unroll fabric or rubber for precise cutting. Laser cutting is used for thin synthetic materials and mesh fabrics like prime knit, as well as for intricate designs requiring high precision. Mechanical cutting is performed using press cutters or automatic knives following program templates. This method is ideal for leather components and thick fabrics. High-precision computer numerical control cutting machines can simultaneously cut hundreds of pieces from different materials, significantly accelerating the process. To minimize waste, software analyzes the most efficient way to position shapes on the material. Leftover scraps from cutting may be used for smaller components or other shoe models. Some recycled materials, such as Parley Ocean plastic, undergo secondary processing for reuse in future products. After cutting, components undergo additional technological treatments to achieve the required properties. Lamination is used to reinforce fabric and improve its performance characteristics. For example, running shoes may feature multi-layer lamination to enhance waterproofing and durability. This process includes applying special polymer coatings or thermal adhesives to increase material strength. Some shoe elements, especially those containing thermoplastic components, go through a heat molding process. When heated to a specific temperature, the material becomes pliable and takes the desired shape. Once cooled, it retains its structure. This method is used to create rigid heel cups or supportive inserts in the sole. Adidas employs several branding techniques for footwear. Thermal printing embeds logos and textured patterns into fabric or leather under high temperatures. Embossing creates raised logos on leather and synthetic components. Embroidery is used on textile models, such as the Stan Smith series. Reflective coatings enhance visibility in low-light conditions. Right now, take a closer look at your sneakers and comment on which branding method was used on them. Cutting takes anywhere from several minutes to an hour, depending on model complexity and materials used. Component preparation, including lamination, heat treatment, and logo application, can take several hours to a full day, as some steps require drying or curing time. Can you believe how much time goes into something that seems so simple? Incredible. The entire process is automated, but key stages involve operators who monitor quality and make adjustments. Adidas is currently experimenting with three-dimensional printing of shoe components, which could revolutionize cutting processes. Laser cutting also enables the creation of complex ventilation holes in shoes without additional stitching. Using laminated materials improves waterproofing without increasing shoe weight. After completing all preparatory stages, the finished components move to the next critical phase, sewing and shoe assembly, where they begin to take their final shape. Sewing machines join individual shoe upper parts, ensuring durability and a polished aesthetic. Adidas production lines use specialized automated sewing machines that operate at high speed and run continuously for extended periods. These machines execute various stitch patterns with precision, ensuring both strength and clean seams. As materials pass through multi-step mechanisms, needles create perfectly aligned stitches that form even and neat seams, enhancing shoe durability and longevity. Once all upper shoe parts are combined into a unified structure, the machine completes the final touches, reinforcing stitches, securing details, and performing quality control. Every component is perfectly aligned and interconnected. As a result, nearly finished footwear emerges, transformed into a functional and stylish product through a blend of mechanical precision and human craftsmanship. Some models feature seamless technology to enhance comfort and reduce weight. Soles are formed by molding material under high pressure to achieve the required shape and properties. Once the upper shoe parts are stitched together, the next step is attaching them to the sole. High-quality adhesives are applied to specially prepared surfaces. These adhesives create a secure bond between components, preventing detachment during wear. Next, shoes pass through a conveyor system, where each pair enters specialized pressing machines. These machines use high pressure and temperature to tightly fuse the sole and upper, ensuring a strong bond. The conveyor smoothly moves each pair through multiple stages, from adhesive application to pressing, undergoing a series of heating and cooling cycles to finalize the adhesion process, making the shoes durable and ready for further stages. This was the most unusual tour in the history of this channel. When I first heard about the EnviroFlight farm, a place where they grow black soldier fly larvae for animal feed, I imagined something straight out of science fiction or a horror movie. But what I saw wasn't just fascinating, it was revolutionary for the future of feed. I never thought raising flies could be this exciting. Yes, you heard that right. Flies. Got questions? Of course you do. Stick around to get all the answers. Let's start with the basics. What exactly are black soldier fly larvae, and why are they so special? So, the black soldier fly? Not some action hero from a movie, but a small insect called Hermetia illucens, addresses two major challenges of our time: the feed shortage and the environmental crisis. Its larvae are tiny protein bombs. These creatures consume organic waste and turn it into high-quality feed for fish, poultry, and even pets. Larvae can process up to 110 tons of organic waste on just 2.5 acres of production space in a single month. What's more, they use 47% less water and produce 200 times less carbon dioxide than traditional livestock. EnviroFlight is one of the first companies to scale up this process. I visited their farm and saw firsthand how this ecosystem works. Imagine massive rooms filled with trays of larvae. Smelly? Sure, a bit, but it's more the smell of change, and I'm not exaggerating. The idea of using insects as a protein source didn't just come out of nowhere. It stemmed from global problems that have been brewing for decades: population growth, resource shortages, and the massive environmental toll of traditional livestock farming. But how did humanity come up with the idea of farming flies? People have been eating insects for thousands of years. In many parts of Africa, Asia, and Latin America, it's a normal thing. But until the 20th century, the concept of using insects as feed, instead of food for humans, was almost unheard of. Let's be honest, who would have thought, hey, let's raise flies to feed chickens? The first wave of interest in insects came in the 1960s. Scientists started noticing that insects could be a protein source requiring minimal resources. But the idea didn't take off back then. People still relied on traditional methods: corn, soy, and fish meal. Then the modern environmental crisis emerged, forcing researchers to look for alternatives. The Hermetia illucens larvae became the star for a reason. Imagine this: the fly doesn't spread diseases, doesn't buzz around your house like a common housefly, and most importantly, its larvae can digest nearly any organic waste. It's the perfect little recycler. Interestingly, serious research into larvae started in the 1990s, and guess who funded it? Waste management companies. They were looking for ways to reduce the volume of organic waste ending up in landfills. It turned out that black soldier fly larvae could destroy up to 60% of organic material, converting it into protein and fats. That's when scientists thought, what if we used this for animal feed? Around the mid-2000s, the idea of insects as feed began gaining momentum. Picture startup founders in labs figuring out how to grow larvae on an industrial scale. They saw the growing demand for farmed fish and understood, if we don't find an alternative to fish meal, ocean ecosystems are doomed. The first successful projects appeared in Europe and the United States. One of the pioneers was EnviroFlight, which launched the concept of growing black soldier flies on organic waste. Their approach was simple yet brilliant. They created a closed-loop ecosystem where organic waste was transformed into feed, and leftover larvae were used as fertilizer. Let's talk about fish feed because this part really blew my mind. Did you know most fish feed is made from fish meal? Every year, over 15 million tons of wild fish are caught to produce feed for aquaculture. That's an enormous blow to marine ecosystems. Black soldier fly larvae provide an alternative that not only reduces dependence on fish meal, but also helps preserve oceanic fauna. For instance, 1 ton of larvae can replace over 2 tons of fish meal. That's equivalent to saving nearly 5 tons of wild fish. EnviroFlight raises larvae in controlled conditions where they feed on organic waste, leftovers from fruits, vegetables, or even coffee grounds. It's essentially a farm where the animals are tiny but incredibly productive larvae. They're fed, cared for, and when they reach a certain age, harvested, dried, and turned into feed. By the way, the entire process is designed to minimize environmental harm. From every 2 pounds of larvae, you can get over 10 ounces of high-protein feed. For comparison, raising pork requires about 13 pounds of feed to produce just 2 pounds of meat. Here, we've got a product that's several times more efficient than livestock farming. A lot of people are skeptical about the idea of feeding cats or dogs insects. But here's an interesting fact. According to a 2022 study, over 60% of pet owners in the United States are willing to buy pet food made from eco-friendly protein sources, including insects. Black soldier fly larvae have already been included in many premium pet foods. Their protein is not only nutritious, but also hypoallergenic. This is crucial for pets with sensitive stomachs or allergies to standard feeds. When I first heard the buzzing of these flies on the farm, I felt something strange. A bit unusual, a bit eerie, but mostly awe. This is the future we're building right now. I still think this process looks a bit futuristic, but if it's what will save our oceans, feed millions of pets, and make our planet better, I'm all in. How about you? Ready to support the idea of larvae in feed? It's good that humanity finally realizes how much traditional livestock farming drains the planet. For example, raising 1 cow costs the world more water and resources than an entire facility of larvae. People increasingly want to make eco-friendly choices, even in pet food. It's predicted that by the year 2050, Earth's population will grow to 10 billion. Finding new food sources isn't a luxury, it's a necessity. Does this kind of farming have a future? Let me answer that with another question. Does our planet have a future? Because if we don't switch to more sustainable food sources, we're in serious trouble. Right now, farms like EnviroFlight operate in over 30 countries, including the United States, the Netherlands, China, and South Africa. It's estimated that by the year 2030, the insect feed market will grow to $8 billion. Honestly, there's a certain irony to this. We spent hundreds of years trying to get rid of flies as pests, and now it turns out they might save our planet. Life loves surprises, doesn't it? From the outside, a farm like this looks like a cross between a factory and a greenhouse. The main building is modern, clean, and sterile. It's not a chaotic mess, but a high-tech space. The trays of larvae resemble multi-tiered shelves in a library. But instead of books, there are containers filled with wriggling larvae. Automation systems, robots and sensors, control everything from climate to the amount of food for the larvae. This farm isn't a chaotic swarm of flies and larvae. It's a structured system designed for maximum efficiency in farming and processing. It all starts in the fly room. This is a large space with special lighting and temperature control. Soldier flies buzz around in mesh containers or specially designed enclosures. They look pretty unremarkable, black, medium-sized, with long wings. The room maintains a warm, humid climate, perfect for breeding. The main goal here is to give the flies a place to lay eggs. Female flies deposit thousands of tiny eggs into special containers. These containers are wooden or plastic panels with small holes. The eggs are then moved to incubators, basically warm shelves, where temperature and humidity are kept optimal. Within a few days, tiny larvae hatch from the eggs. Next, we move to the larva rearing sector. Rows of trays or containers are filled with organic waste, leftover food, vegetable scraps, grain byproducts, and more. In these trays, larvae crawl around, growing at an incredible rate. They look like tiny, creamy worms that literally turn waste into protein mass. Automated systems for feeding and monitoring are often used here, with special sensors tracking temperature, humidity, and even the larvae's appetite. When the larvae reach the right size, they are harvested using specialized sieves or automated conveyors. Then they undergo processing. The larvae are dried at high temperatures or frozen to preserve nutrients. The dried larvae are ground into powder or pellets, which become the basis for feed. Besides protein, larvae are rich in healthy fats. These fats are extracted using presses and used in feed or for industrial purposes. In the finished goods warehouse, protein powder, fats, and other products derived from larvae are stored before being shipped to buyers. What do rockets and a fabric stronger than steel yet lighter than plastic have in common? And how do engineers create technology that withstands 17 million pounds of thrust, the freezing cold of space, and temperatures in the thousands of degrees? Today, we'll uncover the secrets behind rocket construction, from revolutionary materials to million-dollar final tests. Get ready, this journey will leave you in awe. First off, a rocket isn't just a metal cylinder with engines, as it might seem at first glance. Turns out, many of its components are made of advanced materials called supermaterials. Take carbon fibers, for instance. They're incredible. Imagine a fabric that's lighter than plastic, but stronger than steel. These fibers are woven into thin layers, almost like a carpet, then infused with special resins and baked. This process creates the rocket's body, capable of withstanding extreme stress. Picture this. In just 1 square inch of carbon fiber, there can be up to 50,000 individual fibers. Each one is only a few micrometers thick. That's thinner than a human hair. Let's dive deeper. Carbon fibers are made from a polymer called polyacrylonitrile, or from carbon residue in petroleum. The process begins with long, thin threads of this polymer. These threads are heated to extraordinarily high temperatures, up to 5,500 degrees Fahrenheit. During this process, organic components are removed, leaving nearly pure carbon composed of tiny yet incredibly strong crystals. These crystals in carbon fibers are aligned in one direction, like perfectly arranged bricks in a wall. This alignment gives the fibers extraordinary tensile strength. Plus, they're highly heat resistant, making them perfect for the harsh conditions of space, where temperatures can swing by hundreds of thousands of degrees in either direction. For rockets like the Falcon 9 from SpaceX, carbon fibers are often combined with epoxy resin to create composite materials. These composites are used for fuel tanks, bodies, and even protective shells, anything that needs to be strong yet lightweight. Carbon fibers are produced in specialized factories, most of which are located in Japan, the United States, and Europe. Companies like Toray Industries and Hexcel are leaders in this field. From these factories, the fibers are shipped to facilities where rockets are built. The weaving of carbon fibers happens on specialized machines called automatic winding machines or robotic braiding systems. At the center of the process is a massive mold shaped like a cylinder or cone, which becomes the rocket's body. Fibers are carefully wound around this mold. The winding isn't random, it's precisely calculated. Layers of fibers are laid at different angles to ensure maximum strength and resistance to stress. It's similar to making plywood, multiple layers with different grain orientations, but on a nanotechnology level. This research took me a long time, and I pieced together this video frame by frame over several weeks to show you. I hope you enjoy it. Now, let's see what happens next. After the body is woven, it's time for the resin. Resin is evenly applied to the fibers to create a strong composite. Think of it as gluing layers of paper together, except instead of paper, you have carbon fibers, and instead of glue, you have specialized polymer resins. Once the body is ready, it goes into a massive oven called an autoclave. Here, at about 400 degrees Fahrenheit and under high pressure, the resin hardens into an ultra-strong material. This step is critical because, without it, the body couldn't withstand the enormous stresses and temperatures during a rocket launch. This process typically happens in specialized hangars or production facilities. For example, SpaceX's Gigafactory, enormous, immaculately clean spaces. Robots and automated systems control everything to ensure not a single speck of dust interferes with creating the perfect rocket body. The size of the machines and molds is staggering. Imagine a cylinder tens of feet long and several feet in diameter. Access to these top-secret facilities is required to witness this incredible machinery in action. They say it's a sight that's out of this world. As you might guess, I couldn't see everything with my own eyes. The completed SpaceX Falcon Heavy rocket is 230 feet of pure engineering brilliance. It weighs over 3 million pounds. That's the weight of about 7 blue whales, and can lift 140,000 pounds of cargo into orbit, more than a fully loaded Boeing 737 with passengers, fuel, and luggage. Titanium and aluminum alloys are the foundation for many rocket components that require a combination of lightness, strength, and resistance to extreme temperatures. Fuel tanks must withstand immense pressure and temperature changes since they store cryogenic liquids. Aluminum-lithium alloys, which are lightweight yet incredibly strong, are often used for this purpose. Turbopumps frequently use titanium. It's not only strong, but also highly corrosion-resistant, which is crucial since these components constantly interact with aggressive substances like rocket fuel. The rocket's frame, as well as various mounts and connectors, are often made from aluminum alloys to reduce the rocket's overall weight. But when additional strength is needed, or components face extreme loads, titanium is the go-to material. Some engine parts, such as combustion chambers or structural components, can also be made from titanium alloys. They handle high temperatures and vibrations during engine operation with ease. For reusable rockets like the Falcon 9, titanium is used for legs and parts that ensure reliable landings. For example, the famous titanium grid fins of the Falcon 9 allow the rocket to adjust its trajectory during re-entry. In short, these metals are like the skeleton and muscles of the rocket. One provides lightness, the other unparalleled strength. Next, we were taken to a workshop where every inch seemed to breathe technology. Honestly, I initially thought I had stepped onto a sci-fi movie set. Robotic arms, lasers, and 3D printers creating components from metal powder, all working together like a symphony. These 3D printers are a game changer. Instead of cutting components from blocks of metal, they build them layer by layer. What's fascinating is that this not only saves time, but also allows for shapes that were previously impossible to create. For example, internal parts of fuel pumps are now printed as complex grids, making them lighter and more efficient. And now, the most exciting part, final assembly. Rockets are assembled step by step, the lower stage, middle, and upper stage. Every segment is inspected and tested for proper fitting. Engines are a story of their own. They're installed last, like crown jewels. And these engines, they're engineering marvels. They generate incredible thrust, while operating with the precision of a Swiss watch. Each rocket comprises over 100,000 individual components. Every single one must work flawlessly, because even the smallest mistake can turn a billion-dollar project into a pile of scrap metal. Some rocket components are assembled in rooms cleaner than hospital operating theaters. For instance, satellites or optical instruments are built in clean rooms where air is filtered to remove even the tiniest particles of dust. The staff wears protective suits because even a single speck of dust could damage the electronics or optics meant to function in outer space. Once assembly is complete, the rocket undergoes a series of tests. Picture a massive platform where the rocket is secured and ignited at minimal power. Engineers check everything, from tank pressure to engine behavior. One of the most fascinating steps is simulation. Special chambers recreate space conditions. Vacuum, low temperatures, and radiation. The rocket must prove it's ready for any challenge. Each rocket launch can cost up to $100 million, roughly the price of 50 Ferraris for just one moment in space. Impressive, isn't it? The sound wave from a rocket launch is so powerful, it can destroy not just buildings but the rocket itself. That's why facilities like NASA or SpaceX conduct acoustic tests. Rockets or individual components are placed in special chambers where massive speakers and water cooling systems create a sound that mimics a launch. This ensures the rocket's parts won't break under the immense sound pressure. Acoustic tests are mind-blowing. Imagine a sound exceeding 160 decibels. For context, human pain starts at 120 decibels. These powerful speakers literally bombard the rocket with sound to check if its components can withstand the pressure. Finally, after months or even years of work, launch day arrives. Standing in front of a massive monitor, I felt the world come to a halt. The countdown, the roar of the engines, the clouds of smoke, and the rocket rises into the sky, leaving a fiery trail behind. This is the moment when every bolt, every detail, and the efforts of hundreds of people come together. When a rocket launches, its engines generate over 17 million pounds of thrust, enough to lift an entire island or power a small town for an hour. Before a rocket launch, tons of water are poured under the launch pad. And no, it's not to put out fires, it's to reduce sound pressure. Without this, the acoustic wave from the launch would be so strong it could damage the rocket within seconds of liftoff. When I first set foot in this facility, I had no idea how much work and innovation goes into every launch. But now, sharing all this with you, I'm even more in awe of what human imagination can achieve. Rockets are a true symbol of how far we can go when we set ambitious goals. How do you build an engine that can handle temperatures over 3,200 degrees Fahrenheit and carry a Boeing jet across the ocean? Sounds like science fiction, right? But this is the reality of modern engineering. Imagine this. Every single part, from turbine blades to combustion chambers, is crafted with micrometer precision. Metals that don't melt under extreme heat and 3D printing that's changing the game. Dive into the process of creating the heart of an airplane, where every inch truly matters. This is the magic of technology. Turbofan engines that power sky giants like Boeing and Airbus planes might seem like something straight out of a sci-fi movie, but they're the pinnacle of engineering genius. So how do you take tens of thousands of parts and ingredients, almost like puzzle pieces, and turn them into these incredible machines? Ordinary metals simply won't cut it. These engines have to function in conditions where temperatures soar above 1,800 degrees Fahrenheit. That's hellishly hot, and regular steel just can't take it. Enter titanium alloys, lightweight, incredibly strong, and heat-resistant. For the hottest parts of the engine, nickel-based superalloys are used. And trust me, these are no ordinary metals. They're 21st century alchemy. Carbon fiber composites, by the way, are used in the fan blades to reduce weight while maintaining strength. This extreme heat is generated during the combustion process in the engine's combustion chamber, arguably one of the most critical components of a turbofan engine. Here's how it works. Aviation fuel, typically jet fuel, mixes with air and ignites, producing superheated gases. These gases accelerate to insane speeds and temperatures, often exceeding 1,800 degrees Fahrenheit, sometimes even reaching 2,700 degrees in modern engines. This heat is vital for achieving maximum thrust efficiency. The hotter and faster the gases, the more energy they produce to drive the turbine and propel the aircraft forward. Here lies the ultimate challenge. The engine not only needs to endure these extreme conditions, but also perform flawlessly, without a single hiccup. That's why cutting-edge materials like titanium alloys and specialized composites are a must. They can withstand both extreme heat and intense mechanical stress. You know what's truly mind-blowing about making these engines? Even individual components like turbine blades are crafted with micrometer precision. For example, blades are cast in a vacuum to ensure they're free of even the tiniest cracks. Some blades are designed with a single crystal structure, meaning the metal has 0 seams. But wait, there's more. 3D printing? Yup, it's used too, especially for intricate parts that traditional casting just can't handle. Turbine blades are the heart of the engine. They operate in the hottest zone, converting the energy from the hot gases into rotational movement. First, a wax model of the blade is created. It's almost like artistic sculpting. Only here, precision down to micrometers is crucial. This wax model is then dipped into a special ceramic solution, which hardens into a strong mold. The wax inside is melted away, leaving a perfect cast for the blade. The ceramic mold is now ready for the most critical stage. Now comes the real show. Superalloys, made of nickel, chromium, and other heat-resistant metals, are melted in a special furnace to temperatures exceeding 2000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But here's the catch. It's not just about the material, it's about how it's done. To ensure the blade can handle enormous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams, micro cracks, or grains like regular metals do. Why is this important? In these conditions, seams or cracks are like a ticking time bomb. One small flaw, and the blade fails. Single crystals are grown through a slow cooling process. The mold filled with molten metal is gradually lowered into the cooling zone of the furnace. This process can take days, but the result? A blade that's incredibly strong and durable. Once the metal cools, the ceramic mold is broken away, and the blade undergoes meticulous polishing. A special heat-resistant coating may be applied to help it withstand extreme temperatures even longer. And yes, each blade is inspected individually. Even the slightest defect means it won't make the cut. Fuel nozzles, combustion chamber parts, or even compressor blades in aviation are often made using 3D printing. For instance, GE Aviation prints fuel nozzles for its engines that are 25% lighter, but 5 times stronger than traditional ones. Layer by layer, using powder and light, components are created that make planes fly faster, farther, and more efficiently. First, engineers create a digital 3D model of the part with maximum precision. Every curve and cavity matters. Why? Because these components often operate in environments where even a millimeter can make all the difference, from engine efficiency to reliability. This digital model becomes a map for the 3D printer, which knows exactly where and how to build the required shape. Instead of a solid chunk of metal, ultra-fine powder, made from titanium, nickel, or Inconel, a super strong aluminum alloy, is used. It looks like sand, but the particles are so tiny they're almost invisible to the naked eye. The powder is loaded into a special reservoir, becoming the building material. The printer's working principle is simple yet genius. It melts the powder using a laser or an electron beam. The laser heats the powder to a temperature where it literally fuses into a solid metal structure. Then another layer of powder is added, and the process repeats. This method is called selective laser sintering or melting. And here's the cool part. 3D printing can create even the most complex geometric shapes. For example, components with internal cooling channels that simply can't be made using traditional casting or milling. In conventional manufacturing, you often start with a big piece of metal and carve away the excess. It's not only time-consuming, but also expensive because so much material gets wasted. 3D printing flips the script. You only create what's needed, with zero waste. But the part isn't ready yet. After printing, it undergoes heat treatment, heating, and gradually cooling to relieve internal stresses in the metal. Then comes final grinding, polishing, or machining to fine-tune precision. And of course, every part undergoes rigorous testing. Because here's the thing, if a part fails under pressure, the consequences could be catastrophic. Engine assembly takes place in a massive hangar, where every inch of space is filled with tools, engine parts, and technicians in overalls, all focused on creating something extraordinary. This is the final stage of building an aircraft engine. Here, Individual components, like blades, compressors, combustion chambers, and casings, come together to form a single unit capable of lifting an airplane into the sky. It all starts with the engine casing, a giant metal cylinder that serves as the skeleton where everything else is attached. The casing is made from titanium or nickel alloys because it has to withstand insane forces. Engineers work like watchmakers. The casing is mounted on a massive rig to ensure perfect alignment. Then come the compressors, rows of blades responsible for compressing air before it enters the combustion chamber. Each blade is installed one by one, almost like decorating a giant wheel. Every single blade is manually inspected because even the tiniest defect could ruin the entire assembly. After the compressors, it's time for the turbines. These are the blades that convert gas energy into movement. They're installed with such precision that the gap between the blades and the casing is sometimes measured in micrometers. Next comes the combustion chamber, the engine's hell zone. This is where compressed air mixes with fuel and ignites. Engineers install special nozzles to ensure fuel is delivered evenly, and everything here has to be flawless. A nozzle at the wrong angle could reduce efficiency or even cause engine failure. Running through the entire engine is a central shaft, essentially the backbone. At one end of the shaft is a fan, a massive wheel at the front of the engine, and at the other end is the turbine. When the turbine spins from the force of hot gases, the shaft transfers this energy to the fan, which draws in air. Installing the shaft requires specialized robots. This part of the process demands surgical precision, as even the slightest misalignment can cause vibrations that could kill the engine. Once the engine's internal components are assembled, external systems are added. Fuel lines deliver jet fuel to the combustion chamber. The oil system ensures all moving parts are lubricated. And the electronics? The engine is packed with sensors that monitor temperature, pressure, RPMs, and much more. These systems are attached using cables, tubes, and bolts that must withstand both vibration and extreme temperatures. After assembly, the engine isn't immediately installed on a plane. First, it's mounted on a test stand that simulates real flight conditions, from takeoff to turbulence at altitudes close to 33,000 feet. This is the most spectacular stage. Running the engine at full power fills the air with a deafening roar, audible from miles away, and streams of blazing exhaust gases. The engine is pushed to its limits for hours as engineers test its strength, durability, and efficiency. Once the engine passes all tests, it's disassembled. Key components are rechecked, and then it's reassembled for final delivery. The finished engine is packed and shipped to Boeing or Airbus, where it becomes part of a new aircraft. Piece by piece, engineers craft the heart of an airplane, a marvel capable of carrying thousands of passengers across continents. Isn't this a modern masterpiece? Let us know if you'd like to see more videos like this.